The next talk on in this session is by David Wilkins from Queen's in Belfast, and he'll be telling us about accelerating path integral calculations of vibrational spectra. David, yep, you're sharing your screen. That looks great.
And you can hear me this time?
Absolutely, yes.
Very good.
Looks good. Okay, go for it.
Wonderful. Thanks very much. So it's nice to be here because I live here, but it's also very nice to be at this conference and speaking to you. I'd like to tell you about some work that my group's been doing over the last couple of months. I started on this project in my previous job in Lausanne in the group of Michele Ceriotti, and I've got a couple of collaborators who you might also want to speak to, particularly Venkat, who's here giving another talk right now. And Sam is my PhD student. Jingang is a student in Zurich. So what I want to talk about today is water, particularly the vibrational spectroscopy of water. And as I'm sure you're all aware, this gives access to an enormous amount of information beyond your standard infrared and Raman spectra, which can give you basic information about the structure of water and about its vibrations. You've also got much more exotic methods like multidimensional spectroscopy, as you see here, which tells you about how different vibrational modes are correlated, how they transfer energy between each other. And then things like nonlinear spectroscopy, which we'll also get onto later, that tells you how molecules are ordered at surfaces. So there really is a huge amount of information. And a big problem is to disentangle this, because even from one experiment, there's a sort of a bombardment of information. And this is where I think, and hopefully you all agree already, that atomistic simulations can come in. They can help you make the link between the microscopic motifs and the actual spectral features that you're seeing. But the problem, of course, is that water is really difficult to study computationally. The interactions in it are particularly complex, and if you want to study it using density functional theory, as many people do, you need to have a very specific level of theory. You need to use hybrid functionals, you need to use dispersion corrections to get the hydrogen bonding really correct, and to get the spectra right as well. And it's not only the quantum mechanical nature of the electrons that you need to be accounting for. Water contains light atoms, and the motion of them on the potential energy surface due to the electrons can also be affected by quantum mechanics. What I mean by this is things like zero-point energy. So if you have a reaction barrier and you're not at the bottom of a potential well, it's going to be easier to surmount that barrier. If you're at low temperatures and you can't have a sort of thermally activated reaction, you still might be able to tunnel through that barrier. So these effects have to be accounted for to get many properties of water right, but as I'll show you, particularly the spectra. And I'm going to start with the nuclear quantum effects, which is what I'm going to say the most about. When it comes to static properties of water, we know how to get the exact quantum statistics. I'm not going to show you too much maths. I'll save the details, and I'm happy to discuss this in the question and answer or in a booth later. But basically, to get the exact quantum statistics of a system, all you need to do is replace it by a set of classical replicas of that system. And these replicas have an atom connected to the same atom in neighboring systems by a harmonic spring. And this is an exact isomorphism. You can get the exact quantum statistics. I'm not going to show you the math, but perhaps it's sufficient to see for yourselves that if you have this ring polymer that's spread out, even though it's classical, it's mimicking quantum dispersion in some way. And this is able to account for zero-point energy and tunneling kind of effects. But while this is exact for static properties, we don't have an equivalent, easily implemented method for dynamical properties. And vibrational spectra are dynamical properties. They depend on correlations between the response of a system to an electric field. So you have to make approximations. And there are a few approximations that one can make. I'm not going to focus on any one, because what I'm going to show you is something that's quite general and that can be applied to several of them. But just for the terminology, ring polymer molecular dynamics is what you get if you take this classical ring polymer allow it to run through time and use its dynamics to approximate the exact dynamics. And centroid molecular dynamics is what you get if you use the potential of mean force on the centroid being the center of mass of the ring polymer, to approximate the potential energy. And these are lovely methods. They give us access to all sorts of things that we wouldn't have had otherwise, but they do add a bit of extra complication. Over the past few years, and even decades by now, people have been improving on path integral molecular dynamics, which you remember is for static calculations. And there's plenty of ways to speed these calculations up. But the real problem is that these methods tend to interfere with the dynamics of the system, which makes them unsuitable for calculating dynamical properties, or on the face of them. But I'm going to show you a way that two of the most popular of these methods can be adapted to get dynamical properties back. And again, I'll give you a bit of a whistle-stop tour of these, but I'm very happy to discuss them further later on. So the first of these is to get dynamics from thermostatic calculations. You all know that the amount of quantum mechanicness, I don't have a good adjective for this, the amount that a vibration is quantum mechanical depends on its vibrational frequency. If you have quite a low frequency vibration with a small 0-point energy, the classical, this is the distribution of positions at equilibrium, the classical distribution is very similar to the quantum one. So you could mimic quantum mechanics very well for a low frequency vibration by resorting to classical mechanics. But if you have a high frequency vibration with a high 0-point energy, your classical distribution in blue is much narrower than your much broader quantum mechanical distribution, which is the dashed line. And one way to think of the difference between them, not as naive a way as it might seem, is that you can get from the classical distribution to the quantum mechanical one by raising the temperature. If you have this vibration and you simulate it at a higher temperature, you could get a quantum mechanical vibration. So the amount by which you would need to change the temperature depends on the vibrational modes, the vibrational frequencies, excuse me. And this is the reasoning behind the generalized Langevin equation thermostatin, which has been introduced, which was introduced about 10 years ago now, I guess, which lets you fix the temperature of different vibrational modes differently. So higher frequency vibrational modes can have their temperature fixed at higher values. And the reason that you can do this is because I guess you're all familiar with the Langevin dynamics, which is based on a sort of white noise interacting with your system. The generalized Langevin equation has a colored noise, so different vibrational modes can be affected differently. And if you were to fix the effective temperature of different vibrational modes in a different way, it turns out that you can make path integral calculations converge faster. You can get by using much fewer of these replicas of your system. You can get exact results much more quickly. But of course, and I'll just introduce what I think is a lovely acronym, these path integral generalized Langevin equation thermostats, or piglets, disrupt the dynamics of the system. And this isn't just for path integrals, of course. If you have aggressive thermostating of any system, you're going to affect its dynamics. But it turns out that for this, the effect of the GLE on the system is known. It's a known quantity. If you get a spectrum that comes out of this thermostatic calculation, then you know, or you have an equation for how you got there. This would be the microcanonical density of states and the oscillator strength. And this is a horrible quantity that nonetheless is known. It just depends on the setup of your generalized Langevin equation. So it's kind of an inverse problem. If you apply a deconvolution algorithm, you can get the microcanonical density of states from the piglet thermostatic spectrum, and from this you can get the spectrum. And you can sort of wash back out all of the disturbing effects of the generalized Langevin equation thermostat, which is nice. There's another method that I'm going to introduce, and then I'll start to talk about something else, don't worry. So standard path integral molecular dynamics takes this Boltzmann operator, which, as you can imagine, would turn up pretty much everywhere when you do quantum statistical mechanics, and splits it in a particular way. If you take the equation and write it like this, where beta n is just beta over n. Beta is the inverse temperature, so it's kind of a Boltzmann operator at a higher temperature. Then you can use this so-called Trotter splitting, an approximation for the Boltzmann operator that converges reasonably well with the number of replicas. If you use enough of these ring polymer replicas, then you get something where you can ignore this correction. And it's this expression here, you take my word for it, but we can go through the maths, I'm very happy to. It's this expression here that gives rise to this sort of set of replicas, because you've got n sets of this operator, basically. Now, you might be asking, can you split the Boltzmann operator in a different way? You'll be much more happier if you don't ask it, because the answer is yes, but the maths is horrible. So I'm not going to show that. But if you were to split the operator in a higher order way, you would have something that converges faster with a number of replicas. There are some slight downsides. For example, instead of each replica feeling the physical force due to whatever force field or density functional theory you're using, it feels a force that depends on the number of the replica, so whether it's odd or even, and that also depends on the Hessian rather than just on the potential. And that really does seem annoying at first, but this is something that finite differences can do pretty quickly. So higher order path integrals are great for static methods. And they give exact results, of course, to static methods. But when you look at dynamical properties, again, they perturb the dynamics. If you look at just a harmonic oscillator, things are fairly straightforward. It's fairly straightforward to understand how they perturb the dynamics. The Hamiltonian that describes the energy of this harmonic oscillator, the higher order Hamiltonian, differs from your normal path integral Hamiltonian, oh, my apologies, only by having a larger vibrational frequency. So this should be W0. What I'm trying to say is that the higher order Hamiltonian for a harmonic oscillator is very similar to any other Hamiltonian for a harmonic oscillator, but the frequency is blue shifted. And it's blue shifted in a way that we can correct for. If we take a spectrum that comes from harmonic oscillators and red shift it, we could get back the correct vibrational spectrum. Now, water is not harmonic, it's very anharmonic. If you think about the OH stretch, that's a particularly anharmonic mode. But as I'm going to show you, using this redshift even for anharmonic systems does pretty well, happily. So the other thing that I told you was a problem for describing water, and I'm going to go over this reasonably quickly, is the electronic structure. Water's properties are sensitive to the level of electronic structure theory that you use, but happily, there's many high-quality machine learning force fields. And you've heard a lot about machine learning over the past couple of days, so I'm not going to labor the point very much here. But we used a couple of neural network potentials which avoid having to carry out DFT calculations to get the energies and forces, which is already a massive time save. But that's not the only place where you need electronic structure theory. The vibrational spectra are related to correlation functions of your response to an electric field. So the infrared spectrum is related to this time correlation function of the polarization of the system, its bulk dipole moment. And similarly, the Raman spectrum is related to the same for the polarizability. Now you can get the polarization from ground state calculations, but the polarizability needs you to go to excited states. And in any case, if we're going to use machine learning for the force field, we don't even have ground state calculations. So can we machine learn dielectric responses? I wouldn't ask you if the answer was no. There is a method that I have developed, and this makes use of the fact that the response of a molecule or material to an electric field is a tensor. When you rotate a system, that response rotates covariantly. If you take this weird organic molecule here and rotate it, the polarizability tensor will rotate covariantly. And because we know that our electronic responses have this property, we can build this into the learning. So I'm not going to go into any details because I'm aware that we're a bit tight for time, but I do advise you to have a look through these two papers, particularly the second, which is a very recent review, and that shows how this symmetry adapted learning is basically a generalization of your standard kernel-based methods for predicting properties. Let me show you some results now. Just very briefly, the details, just so that they're up here somewhere. Whenever we used a neural network force field, it was parameterized to these two levels of theory, which is hybrid DFT with dispersion corrections. Higher order path integrals, where we used them, involved a fourth order splitting of the Boltzmann operator, which is named for Takashi and Imada, so TI. And the symmetry adapted Gaussian process regression, the symmetry adapted machine learning, used a training set with 1,000 water boxes from replica exchange dynamics. And they were trained with data that we got from Quantum Espresso at this particular level. And I'm going to start just by showing you that these machine learned responses are good, that before we do anything else, they work. I'm going to show you what's called learning curves. I don't know if you'll have seen them over the last couple of days or in the past, but basically this shows you the error in predicting a property as a function of the number of points that you use to train your machine learning model. And this shows, it shows that it's working. You've got something where the error in predicting a property decreases as you use more molecules to train the model, more systems to train the model. And you've got something where our best model has predictions that are pretty close to a straight line. So on the x-axis is the prediction, on the y-axis is the calculated response property. And the error for the polarization for the bulk dipole moment is about 1% of the variation in the training set polarizations, which is great. And for the polarizability, it's about 11%. It's actually quite a standard thing that polarizability is harder to learn than polarization. But this is still quite good, I would say. You can see for yourselves how well it clusters around this straight line. Okay, so let's show how well it's going to do for spectra. We're going to start by looking at thermostated calculations, which have been deconvoluted. And I'll start off by just showing you the vibrational density of states, which is the Fourier transform of the velocity-velocity autocorrelation function. I'm going to show you here the results from thermostatic ring polymer molecular dynamics, which is what we're aiming to get close to, and the deconvoluted Piglet thermostat. And you see that it does reasonably well. The Piglet thermostat has a little bit of a redshift compared to ring polymer dynamics, and it doesn't do so well at low frequencies, which we'll actually discuss a bit further later on. But for both water and ice, it's doing reasonably well. So, sorry, my mouse is going crazy. So given this, let's combine the vibrational dynamics, which we're doing pretty well at, with the responses and get some vibrational spectra. And here we have the infrared spectra of water, where we include the dielectric response and the vibrations. And you see that at both these levels of neural network, we're doing reasonably well. The OH stretch is pretty good. The librational modes at low frequencies are also pretty good. The main problem is this bending mode at the mid-frequency range. And I can happily tell you that this isn't a problem with the symmetry adapted model that I trained. It's actually a known problem with the neural networks. They do slightly redshift and broaden this band. So that's the reason why it's not perfect with spectra. And then if we go on to Raman spectra, we see something completely different. The stretching mode is reasonably well described by Piglet. But for the low frequency modes, we do quite terribly, to put it nicely. And the reason for this comes if you look at the y-axis. This is actually a logarithmic scale. And the deconvolution algorithm that we used manages to do pretty well for the high frequency and high intensity band, but it produces noise that really washes out the spectrum at low frequencies. So the deconvolution is the problem. And another potential problem with Piglet, beyond this deconvolution noise, is that the method we've chosen is only usable for positive definite spectra. So that's fine for infrared and Raman, but things that can have negative parts like multidimensional correlation spectra or non-linear spectra might be a problem. So I'm very briefly going to show you how we surmounted that. And that's with the higher order path integrals, which don't have any of these deconvolution problems because they don't rely on deconvolution. Firstly, we start with the density of states. Again, the gray curve is what you get from ring polymer dynamics. And all of the other curves show what happens if you take TI ring polymer dynamics and use more and more beads. And what you see is that we can converge on the ring polymer dynamics results, and we can converge on it using much fewer replicas than we needed. sorry, P is actually what I've called N in previous slides, my apologies for that, than we needed before with ring polymer dynamics. And this is great. Even though water is not a harmonic substance, even though it's anharmonic, this correction where you take the disturbed dynamics and redshift them back works really well. So perhaps high order methods are viable. The infrared and Raman spectra are, again, they're pretty nice. Firstly, if you compare the red result to the blue result, red is pure classical dynamics and blue is path integral, ring polymer dynamics. You see that including nuclear quantum effects with path integrals gets you closer to experiment in all cases. And comparing the blue with the green, comparing the blue with the green, you see that particularly for Raman spectra, the higher order path integrals, which are the blue, do much better than the thermostated and deconvoluted spectra, which are the green. Raman is now pretty well reproduced across the entire frequency range. And I'm going to show you one more brief example, and then I'm done. And that's nonlinear spectroscopy. Some frequency generation where you shine infrared and visible light on a sample, and you get a nonlinear response only where there's no centrosymmetry. So that's at an interface, for example.
You've got about 1 minute left, thank you.
Okay, my apologies. I'll try and be done in 30 seconds. And this can be calculated with a cross-correlation function between the polarization and the polarizability. So it's not positive definite, so the Piglet method couldn't do it. And I'll just show you the results, and then we'll actually be done. Classical molecular dynamics is the red, as before. Centroid molecular dynamics is the green, and it's much closer to experiments, so we need these quantum effects to get the experiments right. And happily, higher order path integrals get you pretty close to the full centroid molecular dynamics result. So this is a really heartening outlook for the future, I would say. My hope, and I'll leave this up, is that this will open up the possibility to simulate experiments that we couldn't do before, that include both electronic and nuclear quantum effects using machine learning and higher order path integrals. So beyond surface sensitive spectra, we can do multidimensional spectroscopy as well, which I haven't shown here. And my apologies for running over a little bit. I'll stop there.
Thank you very much. So if folks would like to type any questions into the Q&A tab, while you're doing that, if I can sort of ask a quick question, have you? I know you're doing spectroscopy, but the structure of water is really quite a complicated thing, particularly you're just above 0 centigrade. As it all gets denser and less denser and all that kind of stuff. Have you gained any insight into sort of the structure of water while doing this work?
Not this work in particular, but path integrals have been used to elucidate the structure of water since about the 1970s. So with my work, I haven't made any new or found any new knowledge, but certainly it's what has to be done to get the structure of water right.
Okay, thanks. Do you have any questions before we move on to the next speaker? Here we go. There's a question popped in. How would you consider the coupling for the 2DIR? Okay,
so I deliberately didn't show any 2DIR experiments. We did do what's called a correlation spectrum, which is a sort of beginner's version of 2D infrared. But this is a different thing. This just shows how different vibrational modes are correlated in terms of time. It is possible to do 2D IR with these kinds of methods. There's quite recent work. I can't remember the reference, but there's quite recent work about how you would use path integral methods to do the kind of multi-time correlation functions that you'd need to get 2D IR right. So I can't tell you off the top of my head, but if I note down your name, I'll get a reference to you a bit later on, if that's okay.
Well, thank you again for your talk, and let's switch around to Zach, the speaker. Let me just press a couple of buttons, and I think that's worked. Yes, we see your screen there, Zach. And so This is Zachary Goodwin from Imperial, and he'll be talking about the importance of long-ranged electron interactions for the magnetic phase diagram of twisted bilayer graphene. The stage is yours, Zach.
Great, thank you. Yeah, so first off, I'd like to thank the organisers for setting up this conference, and my collaborators, Leonard, Valerio, and Chia, for performing the work that I'm going to present today, and supervisors Dante, Arish, and Johannes for kind of guiding us through this work. So today I'm going to talk to you about twisted bilayer graphene, so I'll give you a little introduction on that material first. So to create the material, what we do is we stack 2 layers of graphene on top of each other. And so we can start from an AA stacked bilayer graphene, and we can introduce a relative twist angle between these 2 graphene sheets to create this emergent moire honeycomb pattern. And this moire pattern is characterized by a stacking sequence which varies throughout real space. So as you can see, in certain areas of space, we have AA stacking between these bilayers, but in other regions of space, we either have AB stacking or BA stacking. And so what happens to the electronic structure of these graphene layers upon stacking and twisting them? Well, simply what happens is twisting one layer relative to the other one shifts the Dirac cone of one of the layers in momentum space relative to the other. So what we have, if these graphene layers don't talk to each other, is just 2 Dirac cones shifted in momentum space. But because these graphene layers are stacked on top of each other, they can hybridize with each other, and this kind of causes the spectrum to change slightly. So when we twist the angle by a very special twist angle, which is referred to as the magic angle, which is around 1.1 degrees, the momentum misalignment between these 2 Dirac cones matches the hybridization energy, and we get the emergence of extremely flat electronic states near the Fermi energy. Right, so if we look at a bit more of a realistic calculation for that, which is what I'm showing on the left-hand side here. So this is for an atomistic type binding calculation. So what we see here is we get these flat electronic states around 1 degrees, and these are to lowest order, can be considered as kind of graphene states, but with an additional degeneracy factor. So these flat bands can host a maximum of 8 electrons, and at charge neutrality, they have 4 electrons sitting here. So in this electronic structure, what we have is at the K and K prime points, there are Dirac cones. Closer to the M points, we have the Van Hove singularities. So this is quite similar to graphene. And then these flat bands have gaps between all the other bands as well. So they're energy separated between all the other states. And so the bandwidth of these flat electronic states vanishes towards the magic angle, which kind of indicates that the kinetic energy of these electrons are going to vanish, and the dominant energy scale is going to be the electron interaction energy. And when that occurs, kind of suggests the onset of strongly correlated phases. And in 2018, it was in fact found on fabricating one of these devices, magic angle twisted bileographine, performed by Yuan Cao at MIT. They found is there was an onset of correlated phases. So their transport experiments basically found that at charge neutrality, they do in fact find features consistent with a Dirac cone. And upon removing 4 electrons or adding 4 electrons to the system, they find strong band insulating features as well. But in addition to these features, they also found correlated insulating states upon doping the system either with +2 or -2 electrons in the system. So this is where you would expect to find the Van Hove singularities in the non-interacting electronic band structure, which would have a high density of states and a high conductance. But at their experiments, at low temperatures, they found these correlated insulating states. And this generated quite a lot of interest. But moreover, subsequent experiments performed by them found superconductivity in proximity to these correlated insulating states. And this generated really quite a lot of excitement in the field of two-dimensional materials and strong correlations. Yeah, and so to understand these phases, I mean, one of the methods that one might use to investigate the electronic properties is an ab initio approach. But in fact, there are quite some challenges with doing this because at the magic angle of twisted bilayer graphene, there are about 12,000 atoms in the Mori unit cell, which has a length scale of about 10 nanometers. So using a standard DFT code is quite unfeasible to kind of routinely investigate the electronic properties of this material. And as an example, I can say, show a published abstract, basically shows that doing a geometry optimization for a magic angle system requires about 6,000 cores for about 30 days, which is really quite a heroic effort to investigate this material. So, I mean, we essentially want to have an interacting theory that is significantly cheaper than ab initio calculations, but that still retains some of the atomistic information that an ab initio approach would have. And that's essentially the method that I'm going to describe to you today. Right, so first off, what we need to do is generate a commensurate Mori unit cell, because actually certain twist angles don't generate structures with translational symmetry. And then what we do using classical force fields is relax these geometries, because as I was mentioning at the start of the talk, the stacking sequence changes throughout the Mori unit cell. And this, because of this, the interlayer spacing of these the graphene sheets changes throughout space quite substantially. I mean, this is a schematic and I've exaggerated the effects here, but it's just to show you the kind of effect that can happen. And this causes the formation of those band insulating states that I was mentioning. So this is really quite some essential physics to include in the model. And then using these atomic positions, we have a atomistic type binding model to investigate the non-interacting electronic structure of this material. And the hopping parameters for this model are basically fitted to DFT electronic band structures of graphene and bilayer graphene. Right, so then we want to look at the interacting properties of this material. So we did this by developing a atomistic Hartree type binding theory. So what we do is we start off with our non-interacting Hamiltonian, and we construct the electron density of this system, which we can then use to construct the Hartree potential that the electrons feel. And that can then be included as an on-site energy in our Hamiltonian. And essentially we need to self-consistently solve this system of equations, which is fairly expensive to do with Hamiltonians that are the size of 12,000 by 12,000. But to kind of put it in comparison with ab initio methods, I can do this self-consistent calculation on a single node with about 40 cores in about 2 weeks. So that's substantially cheaper than using a DFT code. Right, so we can look at the results of this interacting theory. So in the top panels, I'm just showing the type binding results. So there are no electron interactions in this theory. And essentially what doping does to this system is just changes where the Fermi energy resides in these flat electronic states. In contrast, upon including these Hartree interactions, what we find is that there is an extremely sensitive dependence to the electronic structure on the doping level in the system. And what happens is that when I add electrons to the system, so if I'm adding 1, 2, or 3 electrons, the states at the edge of the Brillouin zone, so M, K, or K prime, these shift up in energy relative to the states at the center of the Mori Brillouin zone. But for a twist angle of 1.4 degrees, which is somewhat away from the magic angle, these effects of the electronic interactions are fairly weak. But as we go to a twist angle closer, so say 1.2 degrees, these interactions become a more dominant energy scale, and what we find is that they induce interaction-driven band flattening, in addition to the band flattening from the twist angle. And right at the magic angle, these electron interactions are actually the dominant energy scale. As you can see, the electronic band structure changes really quite significantly. Right, so now we want to kind of investigate the role of these electron interactions on the magnetic properties of the system, and even actually performing a mean field analysis like the one I've just presented for Hartree theory with a Hubbard interaction 2 is prohibitively expensive. So instead we decided to calculate the magnetic susceptibility of the system. And when the susceptibility diverges, it kind of indicates the onset of magnetic order. And what it can do is it can tell us the critical on-site Hubbard parameter required for magnetic order to occur. And so in graphene, it's kind of known that the on-site Hubbard parameter of the pz orbitals is about 4 electron volts. So we can use this as a kind of criteria for deciding when we expect to observe magnetic order and when we do not. So if our critical on-site Hubbard parameter is larger than 4 electron volts, we don't expect to observe magnetic order, but if it's lower than 4 electron volts, we do expect to observe magnetic order. And it also yields the type of magnetic order that occurs. Right, so what I'm showing here is the results of our analysis in the 2 approximations, so the tight binding without long-range electron interactions and with these long-range electron interactions. And as you can see, the red regions are where we expect magnetic order to occur. So the critical Hubbard on-site interactions lower than 4 electron volts. And you can see that these 2 approximations are really quite different. So in the tight binding, we essentially have magnetic order just right around the magic angle for whole dope systems. Whereas with these Hartree interactions, we have magnetic order over a wider range of twist angles and doping levels because these long-range electron interactions are inducing band flattening in addition to the twist angle. And so we can also kind of extract what magnetic order occurs at each twist angle and doping level. And I'm showing that in the lower 2 panels. So blue corresponds to ferromagnetic order. And this essentially occurs where the bands are the flattest. So in the tight binding case, this occurs right at the magic angle for whole dope systems. Whereas for the Hartree interactions, it occurs over a much wider range of twist angles and doping levels. And in red and orange, we're showing different types of antiferromagnetic order that we can observe. Right, so we can see how well this method kind of compares against experiments. So in an experiment, as I mentioned, the insulating states at plus and minus 2 electrons per mole unit cell are the strongest insulating states. But in our tight binding approximation, we would not expect to observe an insulating state at plus 2 electrons, which is clearly not in very good agreement with the experiments. Whereas when we keep these long-range electron interactions, we do expect magnetic order to occur at plus or minus 2 electrons per mole unit cell. So that's clearly much better agreement than the non-interacting theory. Right, so I'm going to take a bit of a step back and look at the kind of general twist angle and doping dependence of magnetic order. So in the tight binding case, what we find is that as we move away from charge neutrality and magic angle, we expect basically less magnetic order to be observed. Whereas with the Hartree interactions, we actually find the opposite, right? So for larger twist angles from the magic angle, we expect magnetic order at higher doping levels away from charge neutrality. And in fact, subsequent experiments that were performed this year found that our kind of Hartree picture was the closest to the experiment. So for angles larger than the magic angle, significantly larger, the correlated insulating states plus 3 electrons kind of are first observed. The twist angle is closer to the magic angle. We then get the onset at plus 2, plus 1. Yeah, so the experiments kind of confirmed one of the main qualitative predictions of our theory. Right, yeah, so in summary, we've developed a atomistic heart tree theory to investigate magic angle twisted bilayer graphene, which wouldn't really be possible with use of kind of standard ab initio methods. We found that these heart tree theory causes quite large deformations to the low energy electronic structure, as first predicted by Guinea and Valat. So these heart tree interactions induce significant band flattening, in addition to the twist angle band flattening, which further induces the onset of broken symmetry phases. And it appears that these interactions are essential for understanding kind of twist angle and doping dependence of broken symmetry phases in twisted bilayer graphene. That pretty much brings me to the end of my talk, so thank you for listening.
Thanks there, Zach. So again, as usual, if we can get some questions into the Q&A, let me just start by saying, whenever you're doing these sort of things and comparing to experiments, I mean, these must be done experimentally on some substrate or other, I'm guessing. And you're doing the sort of isolated bilayers, I'm guessing, sort of in
Yeah.
Is there any issues comparing to experiment where they have some substrate which is probably influencing some of the results?
Yeah, so there's kind of two factors with that. So in the experiments, they have the twisted bilayer graphene mounted on hexagonal boron nitride. And so there's an additional degree of freedom, like what twist angle do I decide to introduce between the graphene layer and the HBN. Because if I align it, there can be C2 symmetry breaking, which can have quite a big influence. But if you introduce a large twist angle between the graphene layer and the HBN, the kind of effect of the substrate in that sense is quite weak. I mean, explicitly, you probably should have the double Moiré pattern, but this increases the computational expense because you have like hundreds of thousands of atoms in your Moiré unit cell then. And the other effect is actually from screening. Right, so in a DFT calculation, you do something in vacuum and there's no additional screening. But on a substrate, you have screening from the HBN and actually the backgate, which dopes the material. But actually, we found that these heart tree interactions are really quite robust to the dielectric environment. So we can use a metallic gate screen interaction, or we can have a dielectric constant of 4, which models hexagonal boron nitride, and the effects are really quite small on these heart tree interactions.
Okay, yeah, thank you.